Hi and welcome back to the channel. Before we begin, you should stick your phone on silent and close any social media or tabs that you've got open on your computer just to avoid any distractions. We're going to jump straight into this. We're going to look today at something called the conservation of mass. So take a look at these diagrams. What you see here is a chemical reaction where we have substance P adding together or combining with substance Q to produce substance R. Now we know it's a chemical reaction because of this arrow. This arrow says it's a chemical reaction. What do we know so far? Already we know that we can separate this into a left and right side, where the left of the arrow shows us things called the reactants. These are what we start with. And to the right of the arrow shows us what we call the products. And this is what we end up with. This is what we produce. What else can we see? Well, I can see that substance P, what type of substance is it? It's an element. I know this because it's only got one type of atom. Substance Q is also an element because, again, I've only got one type of atom. They're all white atoms, shows us the same type of atom. Whereas substance Q is what we call a compound. We have taken the different atoms we started with and we have formed new groups that we call a compound. Now, so what you can see is that elements have been combined to make a compound in this chemical reaction. What I also want you to notice, and this is what we're looking at today, this is what's new, is that you should be able to see that the atoms involved at the start, all of them are still there at the end. None of them have vanished, and no other new atoms are there. Let's just track this. Substance P, I've got 3 gray atoms. Okay, 3 gray atoms, and each of those are substance P. For substance Q, I've got altogether, I count 6 white atoms making up substance Q. And when they combine, at the end, I've got a total of 9 atoms. That makes sense because if I put in 3 atoms and 6 atoms, I should have a total of 9. What are those 9 atoms made of? Well, I count again, 3 grays and 6 whites, which is exactly what I started with. And we learned before about something called mass. And the mass literally just means how much of a substance you have. And we usually measure mass in grams. Again, that's just a quick recap of what mass is. But mass measures how much of a substance, and we're usually talking about it in grams. Now, 3 atoms like this over here, this is going to have a really tiny mass. So we can just talk about it as 3 atoms. There are 3 atoms of it. There's a mass of 3 atoms. We're not going to measure in grams because we've got tiny, 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 tiny masses. We're just going to deal with atoms here. The thing is that scientists used to think that atoms could like magically be created or destroyed in chemical reactions. Now, of course, if that was true, then the amount of stuff in the world would constantly be changing. If we could create new atoms during chemical reactions, then for all the time that the universe has existed, new atoms will get created every time a chemical reaction happens. And if that was true, then you just have an obscene amount of matter. You know, there'd just be like so much matter around, and it would be constantly getting bigger and bigger. The world would not be very stable at all. Also, if atoms got destroyed in chemical reactions, then the amount of matter in the universe would be getting less and less and less. And over billions of years that the universe has existed, all the matter would eventually disappear. And that is not actually what's happening. What happens is that the amount of matter remains unchanged. Okay? And we say the amount of matter. Another way of saying the amount of matter, remember, or the amount of atoms, is the mass. And it remains unchanged. Unchanged. And another way of saying unchanged, scientists like to use this word conserved. So scientists have this thing where they say that mass is conserved. And all that that means is that the amount of matter remains unchanged, just like we've seen here. that all the atoms are there at the start, just get rearranged and are all still there at the end in a new form. They formed a new compound with different bonds connecting together different atoms. That's all that's literally happened here. Okay, so let's just talk about what that rule is then. Scientists have what they call then the law of conservation. Where does this come from? This comes from this word here, conserved. Law of conservation of mass. What does this state then? It states that atoms, or when we've got a massive group of atoms, we often refer to it as matter. Atoms cannot be created or destroyed they can be rearranged. Now, you've learned about a law of conservation before. You've learned about the law of conservation of energy, which states that energy cannot be created or destroyed, only change from one form to another. Well, this is very, very similar. It's just the law of conservation of mass, and it says that atoms or matter cannot be created or destroyed. They can just be, rearranged. And that is what we call the law of conservation of matter. And what I would like you to do is pause the video, take that down for me. All right, you're ready to do some questions now. Let's have a look at some questions. So here you have questions 1 to 9. It begins with a diagram, the diagram we just looked at, okay? And you're going to go over a couple of questions there that we should have answered most of these for you. So I just want you to now practice applying what we've learned to these questions. So pause the video and do that now, please. All right, a reminder that you should only replay it once you have practiced the questions. Okay, and here are the answers coming up. So these are the answers of questions 1 to 9. What I want you to do now is pause the video and make any corrections. If your answer is not as good as my answer, if you read it and go, no, that's not really what I've said, then you need to make corrections with a red pen. Do that now. Pause the video. Okay, all right, so you guys should be finished that now, and we're ready to go on and look at some examples. Okay, let's take a look at a chemical reaction that I really like to show people in the lab. I'm just going to pause the video for 1 second. I'll be back. Okay, so we're going to take a look at an actual chemical reaction here, and then we're going to talk about the conservation of mass within this reaction. So let's just watch the reaction first. What I want you to watch out for is the chemicals involved and the color changes. Now I'm going to kind of speak over it as we watch the video. I'm going to zoom in as much as I can for you. Okay, so the reaction is between two chemicals called copper sulfate, which is a blue solution, and another chemical called sodium hydroxide, which is a colorless liquid. So this here is the sodium hydroxide, a colorless liquid. Okay, and he's putting a few drops into a test tube. It's a colorless liquid. It would look just like water. You wouldn't know the difference. Now this is a copper sulfate solution, and it's completely clear, and it's like a light blue color. And when we mix them together, what we get, watch the color change. Okay, so what we've started is we now have a darker mixture, a darker blue. It's a much deeper blue than the copper sulfate solution. And I'm trying to zoom in as much as I can. It's a little bit hard to see, but we're actually forming a solid substance in here that's not soluble anymore. So when I said the copper sulfate solution was clear blue, it was blue and it was completely see-through. There was no solid within it. When we've mixed these two things together, we've actually formed this deep blue, and it's like a clumpy solid that's not soluble anymore. I'm going to keep playing, see can we spot the little lumps. If not, I might have to pause the video again and go and get a nice picture of it, of this insoluble solid. But I'm just going to wait and see.
And it's slightly darker blue than
you
it
can
was
kind of see
before,
bits
so
of
we
it
mix
collecting
clear
on the
and
side
light
of the
blue,
test
and we
tube.
got dark
You see the
blue
bits of
chunks.
this blue insoluble substance, these clumps, there you go, connecting on the side of the test tube. So that there is a chemical reaction. Now let's look at what's going on. We're going to write a word equation to describe what's going on. We've got these two substances. We've got sodium hydroxide, and we're reacting it with another reactant that we call copper sulfate. Now, let's just record what these two things look like, the appearance. Sodium hydroxide is a colorless liquid. And the copper sulfate is a blue, clear solution. When we reacted them together, what we found was that we formed, well, I'll tell you what the substances we formed are. Basically, the sodium and the copper are going to switch places here. So we're going to form sodium sulfate, which swap in places with the copper. And the other compound we form is copper hydroxide. So just take a quick look and see what I mean by the sodium and the copper swap places. So the copper then goes and combines with the hydroxide, and the sodium combines with the sulfate. That's basically what's happening here. Okay. And it's this substance, the copper hydroxide, that's actually a bluish solid, which is darker blue, and it's insoluble. It's not a clear mixture anymore, the product. Okay, so that's what we observe when we watch the reaction. Now, I like to do this in class, but obviously we're not in class now, so I'm going to describe how we can use this reaction to watch and observe the conservation of mass. Say we took a conical flask, which is a glass flask with a cone shape. No, I don't want it to correct like that. Yeah. Okay. And into that flask, we're going to put the colorless liquid from above, the sodium hydroxide. This is the sodium hydroxide. And into that, we're going to put a rubber bung, which is just a type of lid, but we're going to trap a string. We've got this string trapped, and this string is wrapped around a small little plastic vial. It's a little plastic container, and inside the plastic container is my copper sulfate solution. So together, they're not mixed together yet. So inside here is my copper sulfate solution. Okay, so we've got these two things in the same container, but they haven't reacted yet. They're kept separate. I'm going to put this on a mass balance. And a mass balance is just a piece of equipment I use for measuring mass. We've used this in class before. I'm sure you all have, anyone watching this video. You put it on a mass balance and say it gives you a reading of 454 grams together. The whole lot together is 454 grams. Now, what we would find is if we let the reaction happen by spilling over the little inside container. So now we've got our conical flask. And our conical flask is still got its lid on, but we've let the string fall down. And now the two chemicals are mixed together. So the vial has fallen over and the copper sulfate has spilled into the sodium hydroxide and they have reacted. And I'm forming that clumpy, insoluble solid. Now, what I would find is if I watch my mass balance, is that even though the reaction has happened, the mass does not change. 454 grams. That's what would happen. That's what I would expect to see because mass is conserved. None of the product escaped or splashed out. I had the same amount of atoms there at the end as I did at the start, so the mass will remain the same. This is something that proves the law of conservation of mass. Now, I would much rather demonstrate this to you for real in class on a mass balance, but unfortunately, I'm not in school and you guys aren't here with me, so I can't actually do that at the moment. But note that that is what would happen. Okay, so we're ready to do some more questions. Let's have a go at these questions. Where are we at? Here. So it's just about that chemical reaction we just looked at. So copper sulfate reacts with sodium hydroxide to produce sodium sulfate and copper hydroxide. Okay, so what you have to do is answer these these 6 questions. So I want you to pause the video and answer these now, please. Okay, so here are the answers coming up. And again, make sure you're correcting them with a red pen. Anything that's not right, you should be fixing, not just leaving it blank. Okay, hopefully you were able to have a good go at these. Okay, and let's have a look here now. Okay, so I've got the first 4 done, and I'm going to do the next 2 live for you. Okay, so the first thing was you had to describe the color. Sodium hydroxide, colorless liquid. Copper sulfate is a clear blue solution. That's how we would describe their appearance. What did you observe when they were mixed together? Well, it turned from a lighter blue color to a darker blue. Okay, so I'm missing a word there. It said it should turn from a lighter blue to a darker blue. And this is important. Some insoluble, which just means that they won't dissolve, lumps were formed. Okay, now there is a word. When we do a reaction and we make an insoluble solid, we call this substance a precipitate. Ooh. Okay, so here's another new key word for you today, a precipitate. And a precipitate is just where an insoluble solid is formed in a chemical reaction. And it's a sure sign that a chemical reaction has taken place. So in the next one, it said, how could you tell a chemical reaction had taken place? Well, first of all, we saw a color change. It changed the shade of blue. But we also saw this formation of a precipitate. Now, you might not have used that keyword there. You might have said an insoluble solid, formation of an insoluble solid. But you could replace that insoluble solid with the word precipitate to make it even more accurate and to use a new keyword that we've learned. Next one, how does the mass change when the reaction occurs? It didn't change. It stayed the same. And hopefully, like that might have sounded like a little bit of a trick question, but hopefully that's what you wrote, that it didn't change, it stayed the same. What about the next ones? The 2 products are copper hydroxide and sodium sulfate. Write a word equation for this reaction. Okay, so think about what we're mixing together. Sodium hydroxide. Sorry, I'm going to have to pause. I think this is going to crash on me. Maybe not. No, it did. Sorry about this now. Okay, and I'm back. Okay, so we have sodium hydroxide is one reactant. I'm reacting with copper sulfate. And it told me what the products were. Here, it told me that I was making copper hydroxide and sodium sulfate. So I'm going to make copper. And if I wasn't sure, I know that these are going to swap places. So copper hydroxide plus sodium sulfate. Great, well done. And the last one says, the formula for sodium sulfate is Na2SO4. Which elements are in it and how many atoms are there of each? So again, it's a little bit of a revision. We're going back a good few lessons here to see if you can figure out how many and which type of atoms are in here. All right, so here I've got the element Na, which is sodium. Sodium. And this 2 means I've got 2 of them. So I've got 2 sodium, sodium by 2. This here is capital S, is a sulfur. There's no number after it, so that's a sulfur by 1. I've got 1 sulfur, 2 sodiums, and then I've got oxygen, O, and I've got 4 of them, oxygen by 4 atoms. You could have also written it like this, Na2SO4. You could have said Na, 2 of those, 1 S, and O, 4 O's. Okay, so 2 NAs, 2 sodiums, 1 S, and 4 oxygens. Again, I have showed you how to do that before. It's a long time ago. I get that, but hopefully you guys were able to remember that, figure it out. All right, almost there now. Let's have a look at sometimes when it appears like our law of conservation of mass gets broken. Okay, so sometimes it might appear like the law of conservation of mass gets broken. Now let's take a look at a case like this. Now, previously, you'll remember this video. I'm not going to play it again. I'm going to remind you though of what we looked at. It was a reaction between magnesium and oxygen, where we burned magnesium, put it in oxygen, and it burned really brightly. We're going back maybe 7 or 8 lessons ago here. Okay. Now, in this reaction, the mass increases. Now, let me tell you why. Here is a mass balance. On the mass balance, in the beginning, a piece of magnesium is measured, its mass. So this magnesium, let's just say it's made of 4 atoms. Just to keep it simple, I'm going to say it's made of 4 atoms. Now, in reality, this piece of magnesium is loads more than 4 atoms. But actually, we're just going to say it's 5 atoms. There's 5 atoms of magnesium. Now, in reality, that piece is millions and millions of atoms. I'm just trying to keep it simple. And when we put it on a mass balance, we get a mass of 5 grams. See, the thing about it is, though, when we measure the magnesium, we're only measuring the magnesium. In this reaction, what the magnesium does is it reacts with oxygen atoms from the air. Here are these oxygen atoms that are mixed in the air. We know air has oxygen in it. We talked about this before. It's what we breathe. And these are going to react with the magnesium atoms. But when we're measuring the mass in the beginning, the magnesium or the oxygen is free in the air. We are not measuring the mass of the oxygen. It is not being weighed because it's free in the air. Now, when the reaction happens, what actually happens is this. Here's our mass balance. Well done. If anybody can remember what the product looks like here, I want you to speak your answer to the screen on 3. 1, 2, 3, go. What does the product look like? All right, if you remember this, well done. It's a white powder. When we burn the magnesium in oxygen, we crumble it off at the end, it's formed like a white powder. Okay, so when we do this and we put this white powder onto the mass balance at the end, what we actually have now is a compound called magnesium oxide, which is where the magnesium atoms have now joined and formed a compound with those oxygen atoms from the air. So this now is what the product looks like. It's a solid made of those magnesium atoms from the metal, but the oxygen atoms from the air are also there. Now, the mass, what will have happened to the mass? This is magnesium oxide. This is the compound. The mass on the balance will go up, say to something like 7.4 grams. Now again, why has that happened? Well, now the oxygen atoms over here that weren't being measured, they are being measured because they're part of the product, the solid product, which is being measured. So again, this might look like the law of conservation of mass has been broken, when in fact it's not. It's just that in the reactants before, we were only measuring the mass of one of the reactants. The other one was not being measured. The mass was not being measured. But in the product, it is being measured. So it looks like the mass has gone up when in fact it hasn't. All the atoms will still be there. There will still be 5 atoms of magnesium, which I've only drawn 4. I suppose I better draw them all in so that I'm not confusing anybody. There are the 5 atoms of magnesium, and we've got 1, 2, 3, 4, 5, 6 atoms of oxygen. So we've got all of the magnesium and all of the oxygen atoms are still there, and the mass looks like it's gone up, but it's only gone up because we weren't measuring the mass of the oxygen before. Now, this can also happen, and this can also happen the other way around. And let me tell you what I mean by this. Say we take a conical flask, and in our conical flask, we're going to do a chemical reaction on a mass balance. We're going to put in hydrochloric acid. hydrochloric acid. That's our liquid. And to our liquid, we're going to put it on a mass balance. To our liquid, we're going to add some powder, and this powder is called calcium carbonate. Calcium carbonate. And we're going to take that calcium carbonate and we're going to add it into our mixture. So now our calcium carbonate is in here. Okay. And as soon as we add it, we're going to see what the mass is of the two reactants together, the hydrochloric acid and the calcium carbonate. Now, let's say when we measure it, it comes up as 50 grams. Now, during this reaction, what we're going to actually get when the reaction between calcium carbonate and hydrochloric acid happens is we're going to get bubbles. We're going to get this fizzing produced in the flask. And that's because one of the products produced in this reaction is a product called hydrogen gas. Oh, no, not hydrogen gas, sorry. It's a different gas. It's called carbon dioxide. Carbon dioxide is a gas, and the gas is going to fizz. These bubbles of gas are going to get produced. Once they get to the surface of the liquid, they're going to evaporate or escape. And of course, they're not going to stop there. They're going to keep evaporating and they're going to leave the container. So the CO2, carbon dioxide, is going to leave the container. So what's going to happen to the mass? The mass, obviously, all of the atoms that were there in the beginning are not there anymore. So some of the atoms from the calcium carbonate and some of the oxygen atoms that are in here are going to escape. So again, the mass is going to go down. After a minute, it might be gone down to 48.5. Wait another minute, it's still fizzing. It might go down to 45.4 and so on. Over time, some of the product is going to escape. So when mass appears to be gained or lost in a reaction, that means that gases are involved. So just like up here, a gas was not being measured. And here, the carbon dioxide, that's also not being measured down here because it's escaping. So generally, if we see something that appears to be breaking the law of conservation of mass, it's doing that because gases are involved. So if the mass stays the same in a reaction, then the law of conservation of mass has been obeyed, and that's because no gases are involved. If the mass increases, it's not because we're creating new atoms. It's because a gas has been added and it wasn't measured in the reactants, just like this one up here. A gas is being added, this red particles. If the mass decreases, it's because a gas has been produced and you haven't managed to trap it produced. Now, if you were clever enough to put a lid on this and stop it escaping, well then all the atoms are still in the flask. So then we would not expect the mass to go down. If you can trap all the atoms, we don't expect the mass to go down. The 50 grams should all still be there in the flask. Okay, so they just get trapped up here, these bubbles of carbon dioxide. Instead, they're not able to leave the flask, that's fine. As long as they don't escape, all the mass will be there. Okay, last few questions. Okay, all right, so there's quite a few questions here, all right, but most of them are pretty short. Okay, so the diagram shows what's happening during a reaction. White circles are atoms of oxygen and the gray ones are atoms of magnesium, or the dark black ones or whatever. All right, so what you have to do is pause the video and first of all, write a word equation for what's going on. Now remember what we're reacting here, oxygen and magnesium. So you should be able to write a word equation for that now. Then you have, I'm pretty sure you guys can handle all these questions, okay? So I'm just gonna ask you to pause the video, work your way through the questions. A reminder, if you're not gonna do the questions, you're not gonna learn as much from the video and you're pretty much wasting your time because you're just not going to commit it to your long-term memory. Okay, so pause the video, make sure you do these now. All right, so you should only be watching now. If you should only be listening to my voice if you've got these questions done. Let's have a look at the answers. All right, so question 1, here is the reaction. We're mixing together magnesium and oxygen, so those are the reactants. The products, we put the, how do we name a compound? We've done this already. You put the metal name first, magnesium. You put the non-metal second, ox, and you end it in IDE. So magnesium oxide, well done. What about using the number of active particles to prove that mass has been conserved? Well, if we count them up, there are 4 rows deep of the magnesiums. So that's 4. And across there are 17, if you counted them. So 4 by 17 gives you 68. So there are 68 particles of magnesium and there are 8 particles of oxygen. When you count them here, they're still the same. There's 64 of those there. Oh no, 68, sorry. 68, still 68, 4 by 17. And there are still the 8 oxygens. So what I've said here is the total number of atoms has not changed. There are 8 atoms, that should say, of oxygen. There are 8 atoms of oxygen before the reaction occurs, and there are 68, oh sorry, there are 8 atoms of oxygen before and after the reaction occurs. So that hasn't changed. And there are 68 magnesium atoms before and after the reaction occurs. Okay, so good job if you said that. Or even if you just said the first bit, that's pretty good. The total number of atoms have not changed. Now, it would be good if you backed up that information with an actual number like what I've done. That would make your answer even better. So you've counted that there are 8 here, and there are still 8 here, and there are 68 of the darker ones, and that is still 68 after. What's the next question? Use the number of particles to explain why the mass of the product is greater than the initial mass of magnesium. Well, when we're measuring the mass of the magnesium in the beginning, we're just measuring these 68 atoms. The mass of the product has these 68 atoms, but it also has these extra 8 atoms combined with it. So let's see what I've written over here. The mass at the beginning is only measuring the magnesium atoms. Only measuring the magnesium atoms because the oxygen is a gas and it's free in the air. To make the product, the oxygen atoms bond to the magnesium atoms to make a solid. And the mass of the oxygen atoms now appears when we measure it. So again, that's quite a detailed description, but hopefully you've said something like that. So really examine it, make sure you've got the bits that in the beginning, you're only measuring the magnesium atoms. When you react it, the oxygen atoms bond and get added to the magnesium atoms. And now when you measure the new mass, the oxygen atoms are going to appear in that mass. All right, the next one, you had a list of steps that happen when we put calcium carbonate in into hydrochloric acid. So the sentences below explain why the mass of calcium carbonate goes down when it's put in acid. You have to put these in the correct order. Okay, so this is what you should have. This is the order you should have. Check yours now. This is the only order that it really makes sense in. Okay, so if you didn't have that, you should fix it. Okay, it doesn't really make sense if you do it any other way. You're not putting them in the right order. It shouldn't make logical sense if you don't do it this way. Let's look at number 5. In a reaction, magnesium is added to acid. So now we're adding magnesium to acid and it starts to fizz. So what does the fizz tell you? It tells you the gas is being produced. What would you expect to happen to the mass? Just like when the calcium carbonate put in the acid and it fizzes, we'd expect the mass to decrease. Well done if you said that. Explain your answer. Why? Well, what's happening? A gas is being produced and it's escaping, meaning there are now less atoms in the container. That's why the mass will go down. Again, good job. Well done if you said that. Lastly, a teacher adds magnesium to a flask and quickly puts a bung or a lid on the flask. What would you expect to happen to the mass now? And again, well done if you said this. The mass would remain the same now because the gas atoms are trapped in the container. They don't escape. So long as they're all in the container, we don't expect the mass to change. It's only if the gas escapes that the mass will go down. All right, guys, that's it. Thanks for watching. I know this is quite a heavy video, so there's a lot of content in here. So well done if you were able to answer the questions. If not, I would suggest you go back and listen to certain bits of the explanation again if there's something that's still troubling you. If you found this video useful and you did get all the questions, or at least you got most of them and you see why you were wrong, please do leave a comment and like the video. It does help the channel. It helps other people to find us and helps other students who might be struggling, who might get help from it the same way that you have. If you have any comments or you'd like me to make any other videos for you, please do leave a comment down below and ask me, and I'll try and get to it as soon as I can. All right, guys, thanks. Don't forget to subscribe to the channel if you want to see more content like this. Thank you, guys. We'll see you in the next one.